The objective of this lecture is to provide an introduction to coplanar impulsive orbital transfer. Now this lecture is going to be part 1 of this topic. And in this lecture, we're going to be talking about the concept of an orbit transfer, and then we're going to also talk about how orbit transfer is accomplished using what are called impulsive delta V's, or what are called instantaneous delta V's. And we're going to then study one particular orbit transfer, which is a 2-impulse orbit transfer, which is called the Hohmann transfer. So the first thing that we need to define in this topic is, what is an orbit transfer? So an orbit transfer is a sequence of propulsive maneuvers that transfer a spacecraft from an initial orbit to a terminal orbit. Now, we're going to be studying the special case of orbit transfers that are called impulsive orbit transfers. So an impulsive orbit transfer is an orbit transfer where all propulsive maneuvers are assumed to be instantaneous impulses. What that means is the maneuver, or I could say any maneuver, any propulsive maneuver is assumed to change velocity instantaneously Okay, say that is without the passage of time. Now, clearly, it's not possible for that to actually happen. But what we're going to do is we're going to make this approximation. And the approximation looks as follows. Is that if at some point on the orbit, the spacecraft is moving with some velocity, I'm going to call it V minus. Everything's measured relative to the inertial frame. It has to be the inertial velocity. And then the impulse is applied such that instantaneously I get a velocity called V plus. Then without the passage of time, this maneuver is referred to as delta VI, and it changes velocity instantaneously, that is, without the passage of time. So delta VI is called an instantaneous impulse. So delta VI is an instantaneous impulse. Now, again, it's not reality that you can change velocity instantaneously, but if the thrust is sufficiently large, then it's a reasonable approximation as a first approximation to consider velocity changing instantaneously. Now, in this particular lecture, we're actually going to be looking at a a further restriction on these orbit transfers, which is we're going to be looking at what are called coplanar orbit transfers. So a coplanar orbit transfer is one where the initial orbit the terminal orbit and the transfer orbit all lie in the same inertially fixed plane. So this diagram actually can be made really nice and simple if we do one more thing. We're going to assume that the initial and terminal orbits are circular. It's important they're circular. So when we do that, we actually get a diagram that looks as follows. So here's the initial orbit, and here's the final orbit, or the terminal orbit. Now, we're going to assume, in this case, we're going to be dealing with the following possibility, because we're going to be simplifying this yet even further, is that we're going to be dealing with what are called two impulse transfers. That's the starting point for all of orbit transfer. So we're going to be dealing with a two impulse transfer. Two impulse transfer. Now if this is a two impulse transfer, imagine that I have an ellipse. I'm going to draw this picture as follows. This ellipse is going to look like so. There's my ellipse. Now that represents my transfer orbit. Now you can see that in order to accomplish the transfer, if I'm doing a two impulse transfer, this ellipse has to intersect the initial and terminal orbits. I'm going to say that the radius of the initial orbit, I'm going to call it R1 because it's a circular orbit. And the radius of the terminal orbit, or the final orbit, is going to be R2. Now, if I'm on the initial orbit, then what that means is that my velocity prior to the application of this first impulse, it has to be at that point that I've marked. It has to be in the direction of the arrow that I just drew. This is equal to v1 minus I. After the application of that impulse, it's going to be in this direction, which I'm going to label as v1 plus I, which makes delta v1 this vector that connects v1 minus to v1 plus. So this is delta v1 I. That's the first impulse. Now, the second impulse is if the velocity of the spacecraft prior to the second impulse is v2 minus I, and the velocity has to be on this final orbit when I'm all done. This is v2 plus I. Then the second impulse has to be the vector that connects these two, which is delta v2 I. Now, that's what the diagram looks like in terms of the two impulses. But we're going to actually work with now a basic two impulse transfer after we've figured out the basic properties that have to be true of the transfer orbit. So this is properties of the transfer orbit. So the first one is, if you look at this diagram, you'll actually see that the periapsis of the transfer orbit has to be less than or equal to the initial radius. If it's larger than the initial radius, it's not going to intersect the initial orbit, in which case it's not going to be a possible elliptic transfer orbit. So as a result of that, we actually get that P over 1 plus E, because that's equal to periapsis, has to be less than or equal to R1, which says that P has to be less than or equal to R1 times 1 plus E. Similarly, if you look at the diagram, you'll see that the apoapsis of the transfer orbit has to be bigger than or equal to R2, which implies that P over 1 minus E has to be bigger than or equal to R2, which implies that P has to be greater than or equal to R2 times 1 minus E. So those are our properties of these different of the transfer orbit in terms of the parameter or the semilattice rectum, and in terms of the two radii of the two orbits. Now, what we're going to do is that these properties here have to be enforced in order for it to be a valid transfer orbit. So we're going to look at the most basic two-impulse transfer that is used quite extensively in orbital mechanics, and it's one that is it's not just that it's used a lot, but it's actually the basis for so much, because it turns out that it's a very useful transfer, both in terms of its structure and in terms of the properties that, if you were to take an advanced course in orbital mechanics, you'd learn something about this transfer that would be very useful. But for right now, it really has to do a lot with the structure. And I'm going to draw the Hohmann transfer first, and then I'm going to describe it. So the first thing is, let's go back to these two circles. So here are our two circles. We have the initial circular orbit, we have the final circular orbit, and these two impulses, it's a two-impulse transfer. The first impulse occurs on the initial orbit, and it's tangent to the initial circle, to the initial circular orbit. So this is going to be delta V1I. Because that impulse is tangent to the initial orbit, it results in a transfer ellipse or transfer orbit that actually takes you up to the other orbit in such a way that it hits the second orbit tangent to the second orbit, from which the second impulse is applied, delta V2I, which places you into the final circular orbit. So each impulse is tangent to the respective orbit. The first impulse is tangent to the initial orbit. The second impulse is tangent to the final orbit, and this is an elliptic transfer orbit. So it's an elliptic transfer orbit. Now, here's going to be the key to being able to do all of this, which is that notice that since the radius of the first orbit is R1 and the radius of the second orbit is R2, that it turns out that delta V1 is applied tangentially, or applied at, the periapsis of the transfer orbit. And similarly, or maybe oppositely, delta V2 is applied at the apoapsis of the transfer orbit. Now, we are going to work our way through these different impulses. So we know that the impulses are tangential, that delta V1I and delta V2I are tangent to the initial orbit and terminal orbit respectively. So as a result, we can actually make the following assertion, which is actually really nice, which is that the magnitude of delta V1 is equal to the change in speed at the initial orbit and the magnitude of delta V2 is equal to the change in speed at the final orbit, or the terminal orbit. Now we can draw this picture again, because we actually have this diagram which gives us even more structure from what we had originally, which is that here's the velocity, or the speed, if you want to look at that, the direction of the velocity. This is, I'm going to call this V1 minus. That's the speed on the initial orbit before the application of the first delta V. But because the delta V is tangential, V1 plus, or the velocity I should say, leads to a maybe we'll just leave it as a velocity for right now, just so that we have this in terms of vectors. So this is V1 minus I, and this is V1 plus I. So this right here becomes, that amount right there is delta V1I. Similarly, now we get up to the final orbit. So we draw this transfer ellipse, we get up here. This direction is V2 minus I. And then when we're all done, we wind up with V2 plus I. So that makes this vector right here, that vector, that is equal to delta V2I. So you can see from this that it's clear that the change in speed, which is delta V1, has to equal the magnitude of delta V1. And similarly, delta V2 has to equal, the change in speed has to equal delta V2I. Now that's not true in general, because if the two vectors are not in the same direction, the difference in the speed is not going to equal the magnitude of the impulse. But it just so happens in this particular case that that is true, because the velocities are pointed in the same direction, both at the before and after the application of the initial impulse and before and after the application of the final impulse. So now what we can do is we can actually use that to our advantage, which is that if you look at V1 minus, that's equal to the magnitude of V1 minus I. And that's equal to the square root of mu over R1, because the initial orbit is circular, so it has to have a speed of square root of mu over R1. Now, let's look at V1 plus. That's equal to the magnitude of V1 plus I. But now that is equal to, well, I can use the vis viva equation to be able to do this, which is, I know that this is equal to the square root of mu times the square root of 2 over R1 minus 1 over A, where A, I'm going to write it here, A is equal to the semi-major axis of the transfer orbit. Now, I'm going to remind everybody of the vis viva equation. I'll put it over here. So the vis viva equation says that v squared equals mu times 2 over r minus 1 over a. So, given the fact that the first impulse is applied at a distance r1 away from the focus, that gives me v1 plus. v2 minus, again, follows the vis viva equation the exact same way, which is this is v2 minus I, And that's equal to the square root of mu. But again, look at where this impulse is applied. It's applied at a radius r, or distance r2 away from the focus. So that's equal to the square root of mu times the square root of 2 over r2 minus 1 over a. And then v2 plus is equal to the magnitude of v2 plus I, which is equal to the square root of mu over r2. And that's the final circular speed. So now we can use this information to be able to figure out what these delta v's are. So let's start with delta v1. So delta v1 is equal to v1 plus minus v1 minus, which is equal to the square root of mu times the square root of 2 over r1 minus 1 over a minus the square root of mu over r1. But now let's look at this transfer ellipse. This is the semi-major axis of the transfer orbit, but you can see that the semi-major axis is equal to r1 plus r2 all divided by 2. So as a result, I can actually put that into this equation, and I get the square root of 2 over r1 minus 2 over r1 plus r2 minus the square root of mu over r1. So now what I can do is simplify this, which gives delta v1 is equal to, I've got the square root of mu times the square root. So let's do this. Let's put this all under one denominator, so common denominator. I've got 2 times r1 plus r2 minus r1 minus the square root of mu over r1, which gives delta v1 is equal to the square root of mu times the square root. Well, I've got 2r2 all divided by r1 times r1 plus r2 minus the square root of mu over r1, which then simplifies to delta v1 is equal to the square root of mu over r1 times the square root of 2r2 over r1 plus r2 minus the square root of mu over r1. Now, I can factor out the square root of mu over r1 to get a result that is even simpler than that. You get the square root of mu over r1 times the square root of 2r2 all divided by r1 plus r2 minus 1. And that takes care of the first delta v. Now we're going to go on and do the next delta v. So next, we know that delta v2 is equal to v2 plus minus v2 minus, which is equal to, well, let's go back over here. v2 plus is equal to the square root of mu over r2. So I've got the square root of mu over r2 minus v2 minus, which is equal to the square root of mu times the square root of 2 over r2 minus 1 over a. So now let's work on this expression a little bit. And we get delta v2 is equal to the square root of mu over r2 minus, well, we've got the square root of mu times the square root of 2 over r2 minus 2 over r1 plus r2, which gives delta v2 is equal to the square root of mu over r2 minus the square root of mu times the square root. Well, let's look here. We're going to put it over a common denominator again. We've got r2 all divided by r1 plus r2. And we've got 2 times r1 plus r2 minus r2, which gives delta v2 equals the square root of mu over r2 minus the square root of mu times the square root of 2r1 all divided by r2 times r1 plus r2, which equals the square root of mu over r2 minus the square root of mu over r2 times the square root of 2r1 all divided by r1 plus r2, which gives delta v2 is equal to the square root of mu over r2 times 1 minus the square root of 2r1 all divided by r1 plus r2. So those are our two delta v's. So let's write them again. So again, we have delta v1 is equal to the square root of mu over r1 times, well, let's go back over here. We've got the square root of 2r2 all divided by r1 plus r2 minus 1. And then delta v2 is equal to the square root of mu over r2 times 1 minus the square root of 2r1 all divided by r1 plus r2. Now, the total delta v is equal to delta v1 plus delta v2, and it's defined to be delta vh, which is delta v for the Hohmann transfer. So that means that delta v for the Hohmann transfer is the sum of these two, which is the square root of mu over r1 times the square root of 2r2 all divided by r1 plus r2 minus 1. And then we've got plus the square root of mu over r2 times 1 minus the square root of 2r1 all divided by r1 plus r2. Now, what we can do with this is we can actually simplify these expressions to make them in terms of a sort of a parameterization that makes it a little easier to understand what's going on. So we're going to actually use the following things. So we're going to parameterize delta VH in terms of the following. One, we're going to do it in terms of this ratio R2 over R1, which is the ratio of the radii. And the second is we're going to use VC1, which is equal to the square root of mu over R1, which is the initial orbit circular speed. So in the process of doing this, we're going to get this in terms of a different form, which will be a little bit easier to work with. So I'm going to do each of the delta v's separately, and then I'm going to add them when I'm all done, because I just think that's a little bit easier to do this. So first, we have that delta v1 is equal to, well, let's just rewrite it just to make sure that we've got everything all in line in terms of what we actually want to do with it. We've got 2 square root of 2r2 over r1 plus r2 minus 1, which is equal to the square root of mu over r1 times. Now what I'm going to do to get it in terms of this ratio r is I'm going to divide numerator and denominator in this fraction by r1. So that gives me 2r2 over r1 all divided by 1 plus r2 over r1 minus 1, which is equal to the square root of mu over r1 times the square root of 2r all divided by 1 plus r minus 1. But square root of mu over r1 is what I called VC1. So that's equal to VC1 times the square root of 2r all divided by 1 plus r minus 1. So there's delta V1 written in terms of VC1 and r. So I can do the same thing with delta V2. So next, I have that delta V2 is equal to the square root of mu over r2 times 1 minus the square root of 2r1 all divided by r1 plus r2. And that is just a repeat of what is there, square root of mu over r2, 1 minus square root of 2r1 over r1 plus r2. But now I'm going to do the same thing. I'm going to divide numerator and denominator in that fraction by r1. So therefore, delta v2 is equal to the square root of mu over r2 times 1 minus the square root. Well, I just have 2 here now because I'm dividing by r1, and I still get 1 plus r. But now, you see that this thing is in terms of the square root of mu over r2, but I want it in terms of the square root of mu over r1 because that's the circular speed on the initial orbit, which I said I was going to get everything in terms of. So what we're going to do is we're going to rewrite the square root of mu over r2. So you get the square root. I'm going to write it this way. Mu over r2 times r1 over r1, which doesn't really do anything. It just multiplies by 1. But that allows us to be able to rewrite this in terms of in a different way, which is that now what I can do is I can rearrange this this term outside, the factor outside the brackets, and I get the following. I get mu over r1 times r1 over r2, and then I get 1 minus the square root of 2 over 1 plus r. But now I can split this up, and I get the square root of mu over r1 times the square root of r1 over r2 times 1 minus the square root of 2 over 1 plus r, which is equal to the square root of mu over r1, and now r1 over r2 is 1 over r. I get 1 minus the square root of 2 all divided by 1 plus r. So now I have it in terms of this circular speed vc1. So therefore, I get that delta v2 is equal to vc1 times the square root of 1 over r times, well, I've got 1 minus the square root, and I've got 2 all divided by 1 plus r. So now you see I have it in terms of what I wanted. So now we can write delta v Hohmann as follows. And this actually makes it quite useful to be able to work with it a little bit better, which is that delta v Hohmann, which is equal to delta v1 plus delta v2, is equal to the following. Is equal to, well, now I've got this in terms of everything I want. So let's go back and get delta v1. I've got vc1 times the square root of 2r all divided by 1 plus r minus 1. And then I've got plus vc1 times the square root of 1 over r times 1 minus the square root of 2 over 1 plus r. Now, you can see that I can divide through by vc1. So this gives delta v Hohmann divided by vc1 is equal to the square root of 2r all divided by 1 plus r minus 1. I'm going to put these in the square braces just because I want to remind myself that that's the first impulse, plus the square root of 1 over r times 1 minus the square root of 2 all divided by 1 plus r. And now you can see that what's happened here is you notice that delta v Hohmann has been normalized by VC1 and has simultaneously been expressed in terms of R equals R2 over R1. We actually get, in that case, that we have a parameterization of the Hohmann transfer impulse in terms of this ratio. Now let's look at a couple of things here just to make sure that that everything here checks out the way we expect it to. So the first is this. So this is important because it allows us to be able to make sure we did everything correctly, which is that you notice that there are two things in these square roots, which is that we've got 2r all divided by 1 plus r. Now it turns out that this is bigger than or equal to 1 for r bigger than or equal to 1. And of course, our ratio has to be bigger than or equal to 1. We're going from a smaller orbit to a larger orbit. So given that we're doing that, it makes sense that our ratio would have to be bigger than or equal to 1. So given that that's true, that means that the square root of 2r all divided by 1 plus r minus 1 has to be bigger than or equal to 0. And that implies, in turn, that delta V1 has to be bigger than or equal to 0. Now, I'll explain the significance of this in just a minute, which is, let's do the same thing for the second fraction there. We've got 2 over 1 plus r has to be less than or equal to 1 for r bigger than or equal to 1. What that means is that the square root of 2 all divided by 1 plus r, well actually let's write it this way, 1 minus the square root of 2 all divided by 1 plus r has to be bigger than or equal to 0 for r bigger than or equal to 1, which implies that delta V2 has to be bigger than or equal to 0. Now, let's go back and remember why this is important. Let's recall that delta V1 is equal to the magnitude of delta V1I. And this has to be bigger than or equal to 0. So we have consistency now. So we've shown that delta V1 is bigger than or equal to 0, which is consistent with the fact that delta V1, the vector, the magnitude of the vector, has to be bigger than or equal to 0. And also, delta V2 is equal to the magnitude of delta V2, I, and we know that this has to be bigger than or equal to 0, and we've shown consistency that delta V2 is bigger than or equal to 0. That's consistent with the fact that delta V2I has to be bigger than or equal to 0. So we have now established a few things that are useful in the construct of this Hohmann transfer. One is that we've gotten it in terms of this ratio R, which is R2 over R1, which is the ratio of the two circular orbits. And we've also normalized it by this quantity VC1. So really what we've done is we have delta V Hohmann divided by VC1 as a function of R. So what that means is that if I tell you what the ratio R is, you can tell me what the size of delta VH is. I mean, of course, given what R is, you don't really need to know what the initial circular speed is. You just divide out through the circular speed, and you get a relative quantity, which is delta VH divided by that circular speed. But now we have a way of being able to parameterize this in terms of that initial circular speed, so we get it in terms of a single variable. So you can think of it as a function now that you could plot on a graph, and you could plot delta V as a function of R and see how it increases as R winds up increasing. So as a sort of going back to what we did in this entire discussion, is that we started with the construct of an orbit transfer, and then we moved on to impulsive orbital transfer. And the impulsive orbital transfer approximation was made based on the fact that we said that the velocity could be changed instantaneously with an impulse. And as a result of being able to change it instantaneously, we constructed what were called the class of impulsive orbital transfers, or instantaneous delta V orbital transfers. Once we did that, we focused on coplanar orbital transfers, where the initial orbit and the final orbit and the transfer orbit are all in the same plane. Once we did that, then we focused on two impulse transfers, which led us into this final discussion, or this discussion which was the basis of this lecture, of what was called the Hohmann transfer. So the Hohmann transfer gives us a two impulse transfer where both impulses are applied tangentially, one at the initial orbit, one at the final orbit. And the whole approach then is, from that point, was to be able to figure out how to be able to describe this impulse in terms of the ratio of the two circles of the two orbits and the initial circular speed. So that was the final result that we got here after we were done with all this. And we also showed that these two impulses were, along the way, were the change in speed because the impulses were applied tangentially. So that gets us to the end of this particular discussion. So we have the basics of two impulse transfers, where the two impulses are designed to intersect the initial and terminal orbits tangent to those orbits on a transfer orbit. Now, there's one last thing that we need to do before we're done, which is recall the transfer orbit. So this is the transfer ellipse, or if you want to call it that, the elliptic transfer orbit. We'll call it the elliptic transfer orbit. And in particular, recall that exactly half an orbital period is traversed for a Hohmann transfer. Well, I should say half an orbital period along the transfer orbit is traversed for the Hohmann transfer. So as a result, the picture, of course, once again, looks like the same picture we've drawn several times, but we might as well draw it again just to make sure. It looks as so. So what is the time required for the Hohmann transfer? This is the elliptic transfer orbit. Given that it's half an ellipse, the time required to complete the Hohmann transfer, so this is the time required to complete the Hohmann transfer. Well, that's equal to, well, one full orbital period is 2 pi times the square root of a cubed over mu. So this is equal to pi times the square root of a cubed over mu, where we remind ourselves that the semi-major axis is equal to r1 plus r2, all divided by 2, and a is the semi-major axis of the transfer orbit. So that completes the entire picture for the Hohmann transfer. We now have everything about the total impulse, and we have the time taken to be able to complete the orbital maneuver and the orbital transfer. So I think that's the place we're going to stop, and we'll pick it up next time with slightly more complicated orbital transfer from the Hohmann transfer.